awesome. We're recording. All right. So let's just have a quick poll. Here we are. All right, so I just want you guys to vote. What would you rather us do first? It's either arrays or logic gates. It's all in the sprint. Let's just do a quick vote.
You mentioned yesterday going over a solution for
Yep.
today.
So arrays.
For yesterday.
So if we do arrays, we would do solution code first, right? Including answering some questions. If we do logic gates, we'll do logic gates, and then we'll do the solution code after the break. All right, cool. Seems like we've made a choice. We'll go for arrays. Awesome. All right. So you guys implemented arrays yesterday. Seems like most of you did fine since you completed the homework. Are there still any questions regarding arrays, how they're implemented, so why we like adding and deleting from the end, but not from the beginning?
Is there any point we'll actually use that pointer arithmetic algorithm or formula in our code this week?
I mean, I don't know. It's up to you. I don't think it's entirely necessary. The thing is, you're already using it when you do pointer arithmetic, right? Like your pointer is the starting address, and then when you add plus 7 or plus whatever, it's doing that. So I guess your question is, will we be implementing it from scratch?
Yeah.
Not really. No worry
Okay.
about it. Okay. All right, cool. Then let's walk through some solution code then. Let me just pull some of it up. All right. Let's see. My computer, and then I just want to make sure. All right, so we're going all the way up to read. Perfect. All right. So let's see. So there's 4 functions we need to take care of for today. Right? Create, append. Create, destroy, append, and read. So let's start with create. These are a little. Hopefully, they were pretty straightforward yesterday. Let's see. Actually, I think we should build this outside. Let me just comment this out. All right. So create array. Let's see. We'll name our array simply array. We'll have it return a pointer to an array. Let's see, Brian, why would we want to get a pointer and not the array?
You said Brian?
Yes, it's Brian.
Why would we want a pointer? Because arrays are all generally pointers, and you point to the start address of the array, and then you can right.
That's one very good reason. Yes, that's I hadn't thought of that, but actually, yes, that's one very good reason. Anything else?
For the function itself.
Yeah. So notice we're not returning an array type. We're creating right. We're returning a pointer.
Yeah, I see.
It's kind of a trick question. There's stuff I'm missing here. So
yeah, I guess I would say just maybe space. I don't know.
Yeah,
there's not a need. I mean, there's not a need to have. I mean, yeah. I mean, I guess just space. Like you don't need. You just need to reference where it starts, right? I don't know.
And so when you have the pointer, right, like you always you have a pretty predictable size for when you declare this, right? Like it's always just going to be the size of a pointer.
Yes.
Now there's something missing here. I kind of cheated and started halfway. I see Vera laughing. Well, wait.
Instantiating a
Oh, the struct.
instantiating a
Yes.
version of the array struct.
Yep.
We don't have the struct.
We don't have a struct, right? Because we're creating this array class ourselves. So yeah, kind of cheated there. Can't really have a type array without us creating the array itself first, right?
Yeah.
All right.
Okay.
So let's create that one first. This here. All right. And so I don't know. Let's see, Michelle. What? Oh no, wait. This one we already have it.
The struct was given. Yeah.
Yeah, you guys got this one.
Int capacity, int count, and
So I'm not actually gonna type it all out. I'm just gonna copy it in.
yeah.
Let's see. I guess we can leave this in. All right. So is anybody that I didn't talk to yesterday want to tell me? I mean, excluding Vera and Connor, right? Why do we have two pointers here? Why do we have two stars? What's going on?
Because the first pointer is the element, and then the second.
When you mean first pointer, do you mean this one or do you mean this one? Left or right?
Yeah, from left to right. So, well, actually, I don't know, but one pointer is going to point to the elements, and then
probably this one.
The second pointer is going to point to I think the many individual pointers that will be the strings that will eventually go into the array.
Yep. Yeah. Pretty close. No, sorry, not pretty close. Just a little confused on the wording there, at least on my part. But you're totally right. Yes, pointing to the strings themselves. That's exactly right. Say let's see. So what would happen if we didn't have the second star, right? Like what would happen if we wrote it out like this?
So that would just be one. It would just be pointing to one array. We would have. I mean, we could have an elements, which would be an array of strings, or rather an array of characters. And so we just have. There would just be only opportunity for one element.
Yep, exactly right. Now, how does that change? Right, so like this is what we see right here, right? Just char elements. You've all done this a bunch of times to declare like one string. Yes, you do have a pointer to the first part of the string, but then all you get is a string of characters. How does that change when we have two pointers here? Let me get you guys out of the way.
So instead of pointing to just one address where it's the start of a character, it's going to point to an array of addresses. So you'll have so yeah, that the first one is it's pointing to the array of addresses. So in every address, that that points to will have an array, or another pointer rather. And each one of those pointers can have a character array, which can be, any length, I guess.
Yep. We're gonna make some here just to illustrate. This could be a really long one, right? You guys get the point. All right. Yeah, that's actually great. Very well explained. Does this is this still confusing for anybody? Or all you guys good?
So just to clarify, then elements is going to be an array of strings, basically, like an array of arrays of characters. That's what that is denoting.
Yeah. So I guess to be more accurate, these no. Oh man. Yeah, my bad. All right, let's change the color then. We'll do it orange. So this would actually be pointing to this first one in the array, right? This one wouldn't be pointing to the middle of the array. It would be pointing like right here.
Okay, so it's like an array of pointers that each point to their own array.
An array of these guys, right?
Okay, cool.
That's a pointer. It points to this one will yes, of course, point to the first one, right? But then these guys, this entire array is like a bunch of these guys.
Okay, that makes sense. I guess I'm not sure how we know this is like multiple elements, like it's how we can tell it's not just a pointer to a single thing, if that makes sense. Like
what I'm hearing is, how do we know when to use a single and double?
Well, just like I wouldn't have been able to tell just by looking at it that it was an array of arrays. So like you have the char star thing is a string typically. So it's an array of characters, but then putting the star in front of the star doesn't seem to necessarily imply that there are multiple pointers there.
So not necessarily, right? The thing is, it points to the first. It points to this first place in memory, right?
Oh, okay. So
you can keep adding more if you want.
That's right. So it's also an array. So it is a contiguous space of memory containing all of these different strings.
Yeah. So think about when you're holding array. So
for pointers, I guess.
So think about how it will work in Python, right? When we talked about arrays, is they have to be one contiguous, right, and two the same data type. And this was due to we wanted to have the same size, right? And so like that sounds all fine, right? And like, all right, this is what we've dealt with before, and like whatever, you don't really think about it too much. But then remember that you're always writing lists in Python that look like different names. Say we started naming people here in the class, right? So we'd have Zach, and we have Brian, right? That's these are all different lengths. My name is a little bit longer, right? Then Michelle, her name is even longer, right? And so it's still an array, but how come all of these guys get to have different lengths, right? Like how are we gonna? So remember that whole spiel yesterday we went on about the size of arrays and how we index it in the start address.
Yeah.
Nice. I'm biased in wanting to bring this back. I just love this too much. I know it's not entirely necessary. I know you guys remember, but start address, right? Like the plus index times times data type size. Like how is, oh man, why can't we see it now? Like how is that gonna work here when this array has a lot of different sizes,
Right.
It doesn't, right? Like it does not. You don't index like that, right? Like you don't go up until H and then figure out that Brian is next and then finish Brian. You do something like this. You have your element pointing to the first string of a pointer. Those are all the same, right? So the first one is pointing to C, to B, to L, to the capital M. And then those you can point to wherever they're really stored in address as an entire. So
Great. Okay.
this one here might be Michelle, right?
Michelle behind bars.
Yeah, it's not that intuitive to think about. I was a little bit lost when I was first looking at it as well. But so try and think. Okay, one just like this right here, right? Like how is this going to work in Python? So like it has to make some sense. It has to make sense somehow, right? Like they make it work.
Yeah.
Same thing with JavaScript. And then the other thing that helps me think about it a lot and makes it kind of pretty easy is to think about what would happen if it were only one star, right? And then from there, at least for me, it feels a lot more easier to build up. A lot easier to build up.
Yeah, I think it makes more sense now. I think I was thinking about it wrong, because the star always sort of implies like a contiguous chunk of memory, so there's always sort of an array implied in a pointer, regardless of the length of the array.
Yes. That and one implied when it's a char star, right? Remember that when it's an int char, not necessarily.
Sure, yeah.
If it's an int char, it might just be pointing to just like that one int.
Yeah. Right, okay.
All right. Just clear up for anybody. Does anybody have any other like, nuancey questions or stuff? I know it's a little bit confusing, so I'm happy to spend a little bit more time on this.
Is there any max depth we can do pointers to? Like,
I don't think
do like char, star.
I mean, I don't think so. I mean, not. I mean, I guess the size of your memory, right? You just like make everything a pointer to one value, but no, I don't think there's an effective limit set by C. Not that I know of. Not that I think anybody like even comes close to it. Right? Like why? I can't imagine a situation where it would make sense to go like past 10 pointers.
Neither can I, but I'm sure someone can.
Yeah.
Vera always says there's always an edge case for everything.
I've worked in the industry. They exist.
Right.
It's just a matter of when.
Yeah, or just clients you don't want to hire and you say like, no, thank you. I'd rather sleep. All right. So cool. We're here. Anybody? So okay, we have our struct. We type def it. We call it here. I remember you can call this whatever you want, right? Just as long as you keep it consistent. But let's just make it simple. So I guess what's next?
Allocate memory for the array struct.
Woohoo! And how do we do that?
Malloc.
Yeah. And now what comes in here? How do we make this really simple? I want Steve to answer this one.
How did I know? Size of array.
Yeah. And so what's the benefit of doing this, Steve?
It's you don't have to do all kinds of addition of all the elements and figure out that there's still not enough space when you do that.
Yeah, no trying to figure out how many pointers I have here inside or wherever. It's just like this struct has a certain size, and like the size of array is giving me precisely the amount of space I need for size of array. All right, and then so we how many elements can this array hold? Remember in C, when you're declaring an array, you you either say how many you want up front, or right, like C calculates it for you, but you know it's always set up up front. So this is why we're hitting capacity. Obviously not count, because what are we going to set count to when we're doing our new array? So capacity, of course, right? We have to state up front how much we want. What about for count? What are we going to set this to?
0.
0.
All right, and then
Just refresh my memory, Luisan. The dot, the array dot capacity, array dot count is the same as array arrow capacity, array arrow count, right?
it's not the same. It's not the same at all.
Oh, okay.
They are
Mine worked
different.
with the arrows.
Yeah,
Sorry?
mine does too.
You guys
Mine
did?
worked. Yeah, I did the arrow.
All right, and tell me, why do we use arrows and not dots?
Small arrow.
Dereferencing.
For no reason, we could use.
Just
No, I'm
whatever
just
you want. Yeah, somebody tell me why. So I guess I'm glad you caught it. This is not right. Well, you should be using arrows.
Oh,
why?
okay. Oh my God, this was last week. Wait, it felt right, so I did it. But
So our
Feline complains.
instance ARR is a pointer to an address and not a direct object itself, and we need to dereference to actually get at those values within it.
Yep. So let's see.
there you go.
So what you see here with the arrow is, and I might get this a little bit wrong, I think, but it's same as doing this, right? Remember, so R here, this is a pointer, right? Like this is not a value itself. There's two little boxes here, right? So this is the pointer.
Oh, I might have
Yeah, go ahead, Steve.
on that. The malloc should be capacity times size of array, right?
Not yet.
Yeah, not yet, but nice thinking. Actually, I'm gonna have to like be clear in my head and explain why, but yeah, not quite yet. Sorry. Okay. So yeah. So here we have the pointer and the value. So if our array is the value, right? Then how we access anything inside the array is with the dot, right? Array the capacity, array the count. Let's stick for those for now, because I don't want to. If, however, we're setting a pointer, right? Let me change this color here, right? Like, so the value. Let me write this first. Actually, it's gonna make more sense. So the value here is the struct array, right? So like the struct here is, and then this has some address. Like this this struct is stored somewhere in memory, like someplace, wherever. And then this pointer, its value, right, is not any struct. Its value is some address, right? Like it has its own irrelevant. It's not entirely irrelevant, but for our purposes now, right? This pointer has its own irrelevant address, right? But its value is some address. So if we have dot array, right, and we try to do on this array that is a pointer, if we try to do dot capacity, what we're doing is we're calling some address dot capacity, right? Let's see, let's bring this down here. And so this some address dot capacity, let's actually change this to blue, so it makes a little bit more sense. Oh man, that's not gonna work. All right, sorry guys. But yeah, but so this sum address, right? Like this array. Oh, they just lose the. Sorry, let me try again. All right, so we have our dot r here, right? Like it's a pointer. It's pointing somewhere in memory. Again, if we do array dot capacity, follow the orange color code, right? Meaning this was a pointer. This is not just any variable. Let's actually call it like this. So it's pointer array. If we do pointer array here and then try to get its capacity, what we're actually doing is something like some address dot capacity, right? So what you actually want to do first is you want to dereference point r. So now instead of being instead of the value being some address, the value is actually struct, right? Like these two are the same. And then from the struct, you're getting capacity, right? When you're doing this, this just has to happen first. And so when we're using arrows, what we're doing is it's just shorthand for this. It just makes it easier. So we can do no need to dereference. We just dereference right away with the arrow, and then we get access to it. So the easy way to remember this is if pointer to struct, then you use arrow. Struct, use arrow. All right. If struct itself, then you can simply use the dot. This is the easier way to remember it. So yeah, a little bit of a long rant there, but yes, we don't use the dot, we use the arrow. Let's get rid of this one, get rid of you as well. And then array kind of. All right. So we set the capacity to capacity. We wanna tell it how much it can hold. Our array, the one array we're implementing. We set the count to 0 because out is how many states does the array currently hold. Currently nothing, right? We just initialized it. And then now we need, so Steve, you were coming to this, right? Like now we need to set space for the elements. So how are we going to set this? I mean, I guess, and anybody can answer, I'm not singling you out, Steve. Just you mentioned it before.
I was actually vaguely curious about this one. I came up with a way to solve this based on a bit of reading, but I don't know if it's necessarily the optimal way to do it.
Sure. How did you?
So what I ended up doing personally was a malloc capacity times size of array elements.
Capacity times
size of array arrow elements.
Array arrow elements.
I'm sorry, not array, ARR.
Oh, yes, my bad. Yeah, that was my bad.
Yeah.
Right.
With the idea here being that the elements array, we want it to be of length capacity with each block being the size of a pointer. And we just happen to have a convenient pointer in the implementation and definition of elements. So I wasn't sure if we could do a char star here or not. I thought about it after I came up with this and I haven't tried it yet.
So actually, yes, let's write that out because it's gonna make more intuitive sense. But this is right. But instead of writing this, you could have just passed this in.
Okay.
Yeah. And awesome. Does this make sense, guys? Is this clear? Why we're doing this?
I did another version of that upon doing some reading. I found out that calloc, there's a
Yes.
calloc, and calloc takes in two arguments.
Mm-hmm.
And since we have two arguments in there that we're multiplying, I basically replaced malloc with calloc and then did capacity, incapacity, and then you put a comma after that and take out the multiplication sign. And that does the same thing, I think.
So what exactly is calloc?
Michelle, do you know?
Hold on.
For those of us that haven't seen that yet.
It does the same thing as malloc, except it takes in, so it's also for allocating memory. It takes in two arguments and what do you call this? It also initializes the allocated memory to 0.
So can you
did
explain
not.
that in English?
Sorry.
Let me not reading it from the text because it's a little bit hard to understand.
I didn't really read deeply into it. I just, when I saw that it takes in two arguments and I knew I needed to do, I needed to have a capacity and the size of the elements, I just plugged it in and I tried it and it worked, to be very honest.
Yep. Let's see.
So essentially, you're basically saying the only difference is that instead of creating spaces with nothing inside of them, it creates spaces with zeros inside of them, with set to 0.
Yeah,
Something like that. Yeah.
Malloc, I think, says this space is for us. calloc says this space is for us, and we're setting it all to 0.
Something like that. Yeah.
Malloc just leaves whatever was there.
It just kind of makes a placeholder, like 0 is like the placeholder until you put the rest in.
So if for some reason you needed a value inside of your empty array or something, or inside of your array, then you would just use.
Or if you wanted to make sure that you had a consistent default value.
Right.
Sorry, real quickly, guys. Can I get rid of this? Is anyone still using this, or is it okay if I let it go?
Let it go. It's recorded.
Oh yeah, it's on recording anyway. Yeah, I guess we can check it later. Yeah, no, what you guys are saying now, it makes total sense. Like I even feel like it's unnecessary to show you, but here you go. When you malloc, you get a bunch of spaces and you have just no idea what there is. What is there. When you calloc, you just set everything to null.
It's not even like a 0, it's just nulled out. Okay.
Yeah, I'm not entirely sure. I've seen different things. Sometimes I've seen like the actual word null. Sometimes I've seen the 0. Sometimes I've seen this null terminator.
It's all the same thing as far as C is concerned, at least.
Yeah. Okay. Yeah. So I've also never been entirely too sure about this. But
it also did say that calloc at most of the time is faster than malloc. That's why I also decided to use it.
Interesting. I don't understand how that would.
Like I said, I didn't really delve into it. I mean, it's interesting enough to go through it later on, but it worked.
Having been in this industry for over a decade, later on often does not come. This
Brian,
sounds interesting. I will read this later.
Yeah.
10 years later, on your bookshelf, still waiting.
Send us the link if you have it, Michelle. I'd love to see why it's faster.
Okay.
Brian, you said you were you going to say something?
I was just gonna say, I was just wondering. I'm trying to think about the purpose of null. So, like, if you needed a value, if you were checking for a value and you were using the malloc array, would you not receive a value back if you try to access one of the indexes of the array? But then if you access the calloc array, then you could access you actually get a value, like a null, like it's
this.
yeah. Go
So when you call malloc, it doesn't do anything with any values that were in that particular spot in memory already. It just says, here is a chunk of memory for your use for whatever. Whereas with calloc, apparently it
returns
does that, but then also nulls out any data that may or may not have been in that block.
Oh. Okay.
Yeah, your credit card number could still be in a malloc.
Okay.
Theoretically.
All right. That makes perfect sense. Okay, so it's actually wiping. It's actually wiping anything that's there. That's what calloc is.
Yeah, it's setting it to not.
Yeah.
Okay.
One thing that helped me understand what was going on is so what you when you throw stuff in the recycling bin, right, and you empty it and you get rid of it, your computer doesn't bother going around and setting everything to 0 again, right? It just removes the pointers basically and tells the computer, if you ever want to malloc this space, it's free for you to use. And so what will happen is if I get rid of this and then I start, adding new pictures, then just whatever I'm storing will overwrite what was here before. And but this won't get set to 0. So when you're mallocing, right, like you've no idea where this is, and this might just be this might just be like an old picture of yours, that you just deleted. You looked goofy or whatever, or the light came out wrong. When you malloc, if you deleted that picture, you might just be grabbing that piece of memory right there and then overwriting it. And so if you check for it, right, like if you check for what the value is there, like there's going to be some value. No idea what it is, nothing related with what you wanted, right? Like you never looked at this, all you wanted was some new empty space to use, but it's not, I guess, truly literally empty with malloc, right? It's just telling you you're free to overwrite this if you want, but the space is yours. With calloc, it's wiping it and it's setting it to 0.
That's illuminating.
Yeah.
Thank you.
There's a really cool project. If I can find it, I'll share it. This woman lost her camera to her camera got stolen, right? And her computer got stolen with all of her pictures, and then the guys that stole it were kind of using it around, and she was so sad trying to get the pictures. Luckily, she was able to get her computer back within like a day. So like not all of it was lost, but then you'll see some of the cool, there's some pieces of the picture, but because they were, I don't know, like doing their own things, they deleted everything, writing their stuff. There's weird looking like lines like this across her photographs. Like they're kind of there, but just like weirdly overwritten by memory.
So by the way, you can X that last comment I did. I'm looking into it now, and more resources say that malloc is faster than calloc because of that extra step of zeroing out.
Yeah, I would have figured as well.
Yeah, that's what I was wondering.
The difference is very, very minimal. That it's so it's funny because those other two said that the opposite, and I was like, okay.
Yeah, all you'd have to do basically is like pass a certain electrical charge specific to that slice of memory, and theoretically it would take a minimal amount of time. But
yeah, but please let's not get into that.
Yeah.
All right, destroy array. So what type of function do you want to return for what data type do you want to return for array, for destroy array?
I don't think we need to return anything.
Don't we just free?
Void.
Void it.
Oh, I'm sorry. Yeah. It's that was given.
Nice, guys. All right, and then I guess, Brian, what do I need to pass in? Should be pretty simple. If I want to destroy an array.
My bad. I was muted. Yeah, just pass in the array, I guess, right? You gotta know what to
Yeah. So what do I type out here?
You're going to type in the array, like the structure array, and then like let it know that it's the structure array, and then
I see.
pointer.
Like this?
Yeah, and then point to the array, a pointer to that structure. So yeah.
All right. Any particular reason
think.
why the pointer and not the array itself?
Because I don't know. In my mind, I'm just gonna answer there's no need, because all you need is the pointer to the beginning of the structure, and then you can access the rest of it. But what is the correct answer?
So that's actually the correct answer. The only part that's missing from that and why it's necessary is, or like super useful, is when you're running functions in C. Whatever you pass in as arguments, you get a copy of that argument. You don't get the argument itself. So if we passed an array, we wouldn't actually get array, right? Let's see, where's the drawing? So if this is our original, right? This is our array, struct array, and then the value here is struct, right? Whatever goes into this into a function is not the original array, is a copy. So let's make that one in light blue.
So if you were to delete that, you would actually still have another copy of the array somewhere.
Yeah.
And if you're just using okay.
Yeah, that's exactly it. And so copy of array R. I mean, I guess this is also a copy. Copy of, right? So when you pass in, when you declare this, right? Like what goes in here is this, right? Like the copy, not this. And so when you pass in a pointer, it doesn't really matter, because even if it's a copy of the pointer, it's still pointing to the same address, right? Vera's not here. We were talking that example with her last time, but if I send you an invitation to a party at my house, right, and I give you the address, and then you make a copy of that invitation and give it to a friend, like even though what your friend has is a copy of the original invitation, like it still has the same address. It still points to the same house, right? Which is very different, right? So like this is why it works, which is very different than, I don't know, like making a copy of my house somewhere else and sending you there, right? Like a very similar house. Yeah. It's not the same thing. Yeah. So yeah, that's why we're passing a copy of the array here, because even though sorry, that's why we're passing the pointer to the array, because even though it's a copy, right? Like how you can photocopy an invitation or you can photocopy an address, even though it's not the exact same one, there's still both pointing to the same place. So there's the pointer here, the original one, it's pointing to the struct. We'll give it a prime symbol to denote that it's a copy. And then the original pointer, right? They're both pointing to the same place, even though they're different things. So that's why it works here.
So you're giving out unlimited number of invitations to people to the house party.
Yeah.
And yeah, gotcha. People you don't like, you just make a duplicate house and you send them there, and nobody will be there.
Exactly. Gotcha. I don't know how you guys do it in the States, but that's how we do it here.
Yeah.
No, sorry, I lost my train of thought. All right, so we have, and then the other thing is, another advantage of passing in pointers and not passing in the struct is this thing might be huge, right? If this is like 1 million items long and we're passing a copy of this that is 1 million items long into the function, then it's going to take 1 million operations to copy. Whereas whenever we're passing a pointer, same thing, right? Like I don't have to build a whole entire house to make the copy of it, right? Like I can just copy the invitation, and then we can all show up to the same place. Same thing. All right, let's see. And so, so we want to go through each of the elements, that we're mallocating, and get rid of those. So that was pretty simple. For int I equals 0. I've seen, by the way, I'm going to take the chance. I've seen some of you guys do something like this, right? Send int I, and then I equals 0, right, to start, and then you can start here, right? So for, I guess, I, and then, you know, I is less than array dot count, and then I plus plus. This is fine. This works, right? And I think I've talked to some of you about it. Just you can also do it here on the on the same line. Just so you guys know, these are both the same. All right. I'm gonna comment these out. Yeah. All right. So let me get rid of these drawings. For n through I up to array.count, right? So we got to get to whatever the however many items we have in the array. Not how many we can fit, but how many there are. And then just call free.
I have a question. In the for loop, the array.count, would that be an arrow pointer instead, or would that be the parentheses and the star, like you mentioned?
You're
earlier?
very right.
That's right.
Thank you for catching that. Yes, and you should all be catching it earlier, guys. Yes, it is an arrow, because we're passing it a pointer, right? We're not passing the struct itself. So very nice catch, man. Nicely done. All right, and then I'll be nice this time. I won't. Okay. So same thing here.
You're a trickster.
I'm gonna make sure you guys are paying attention, because I'm not kind of the douchey college teacher you had.
Douchey.
I'm sorry.
All right, and so remember, we free every individual element, right, inside, and then we free the element itself, the element array itself. Remember, let's see if we can get to those drawings. All right.
End of line 36. What are you doing there?
Line 36?
Yeah. What are you doing there?
So you've allocated some space to the array, right?
With the colon.
Yeah.
Oh, yeah, no, that one I totally missed. Thanks. All right, so this line, what we're doing here is we're freeing all of these guys, right? And so freeing all this. And then finally, in free array elements, we're freeing this one as well, right? Because we have a bunch of arrays there. Let's see, I don't want to lose anything. So we'll just redo everything. There you go. All right, any questions with destroy? Any other mistakes you guys may see? I'm being honest now. Oh, okay, I missed this one.
Is the for loop really necessary? Because when you're destroying the elements in the array, doesn't it destroy the other one that's connected to it?
No, you're just leaving it orphaned. So it's still there. There's just nothing pointing to it anymore. But that space is still mallocked and it's still reserved. So even though nothing's pointing to that space, it's still reserved so nobody else can use it. And that's when that's what you call a memory leak.
So the free array arrow elements on line 35 is freeing up the pointer then? That points to the array that you're clearing in the for loop?
So yes, you're freeing, this one is freeing the main array, like the array of pointers, right?
Oh, okay, gotcha.
Remember there was two arrays, right? Like there was an array of pointers, and then each of those pointers pointed to a string.
Yes, okay, I gotcha.
Freeing the strings here, right? And then, or it was like that pointer, right? These are elements I, so the first one, the second one, the third one, right? We're freeing everything in each of those.
So I have an edge case question when you're done with this particular one.
All right. So we're freeing all of the sorry, I don't know why I get so frustrated when it goes wrong. All right, here we go. And so when you're freeing here, you're freeing each of these, right? Everything, all of the boxes down here, everything that's here, you're freeing those. And then when you free on line 35, then you're freeing this space.
Okay, cool.
Itself. That's the difference. To answer your question, Michelle, if we only freed this, but we didn't free each of the individual ones, then all of these guys down here, they'd be
They're like floating in limbo and not usable.
Floating in limbo, no idea where they are, because now there's no way to find it, because memory is huge and there's no pointer to them, and we have no way to interpret them because we didn't know what type it is. Like there's just zeros and ones. But then we also don't have access to them because they've been mallocked, but they haven't been freed. So
Okay.
it just creates memory leaks.
For line 35, but did we malloc for the elements? We did on line 21. That's where we malloc the elements. Okay, all right. I guess all right. I'm seeing why we're freeing the elements too.
Malloc or calloc, whichever one. But yeah, you guys saw the
right. Calloc, malloc, yeah.
So in the for loop, we're freeing each element in the first array that the point with the, you know how it's a pointer to a pointer on the elements? We're freeing the first pointer.
So
correct?
Let's see. So if all of these have little squares, right?
Yeah.
Yes, when you're doing free elements, you're only pointing to like
you're freeing the first pointer.
The first one. But then
or
there's
the
just
second one.
so
I mean, this is the first array or the second array? The first, right?
Okay, sorry, repeat that question. I think I lost you there.
You know how you have in your illustration, you've got one array on top and one on the bottom?
It's not one array, it's a bunch of arrays.
Okay, a bunch of arrays. So the one that we are freeing in the for loop is the solid array and not the bunch of arrays. And then under it, we're freeing the bunch of arrays.
The other way around. In the array, in line 32, right? So this here is elements. This array right here, right to the right of this is the array elements.
Okay.
And so when you're doing elements I, say we're doing elements 3, right? You're getting to the fourth element, so 0. Oh, wait.
The fourth element.
Yeah, so 0, 1, 2, 3. Yeah. And then you're freeing this array, right? Elements 4 is freeing this array, elements 2 is freeing this one, elements 1 is this one, element 0 is this one. And then this guy right here is freeing the elements array itself.
Okay, got it.
Yeah. So, remember, right? Elements refers to one, let's enclose it like this, like one huge array of elements. And then elements I refers to a different thing. It refers to like one specific value inside of elements.
And that value is an array of characters, correct?
And that value itself is an array of characters. In our case, yeah. Don't want to overcomplicate it, right? Remember that, arrays can be made up of anything. We can have arrays with integers and different kinds of things. But yes, for now, this is enough. This, this serves our purposes. All right, we're going a little long, but I do feel it's been great because we're answering questions. Let me just do then a pen and read really quick before I let you guys off.
My edge case before you move on.
Sorry?
Can I ask my edge case question real quick before you move on?
I do have to ask, do you think it will be instructive to the rest of the class, or is it just fun? Like, if it's just fun, I'm happy to do it. Let's just do it later because we're running out of time. If it's going to help others. But you, sorry?
I think it would be instructive to everyone personally.
Perfect. No, let's do it.
So in the destroy array function you have going on, doesn't the for loop assume that you are mallocing those strings and not just doing something like car star string equals double quote whatever text?
Yes, and actually, thank you for asking that one. The wisest thing would have been to do a check, right? If elements, right? Like, it's not null, or whatever, right? Then we free. Because it might happen that somewhere, some mistake where we made it and something isn't there. It shouldn't happen because we are going up all the way to count, right? We're not going up all the way to capacity. We're technically only writing on those that have been written. We're only freeing only those that have been written on. That's obviously counting on us not making any mistakes. But so yes, those should be there. As for have these always been malloced, we're doing cars, so yeah. To be entirely honest, I'm not entirely sure. So say when you're asking when we do something like this instead of mallocing before. I think, and I'll check. Let me ask because this is a great question, and I'm not entirely sure. Let me copy this. But what I think happens is this mallocs under the hood for you.
Okay.
Right. So I think this mallocs no matter what. So I think that's why.
I wasn't sure if that was like if you freed that since it's doing it under the hood potentially. Since that's the case, if you were to subsequently manually free that and then the underlying like OS something in the compiler or whatever were to try to go back and free it as part of its cleanup of that, would you end up with the weird cases where you've accidentally freed something twice and potentially freed up something that had been reallocated elsewhere?
I mean, again, not entirely sure. It might. So the theoretical answer, I'm not entirely sure about. Please keep it, and let's ask Beach because I do want to know. In case anyone's worried about what's going to happen with your computer, if something like this happens, yeah, no worries. If you free stuff, like if inside your C programs you free something that's not supposed to be freed, your computer is going to be fine. It knows it knows how to handle this. So we'll get the theoretical answer for you after class because I'm not entirely sure. If anyone was worried about something happening, something going wrong with your memory, yeah, no worries, they'll be fine. The program knows that when the C program ends, it knows to free everything that needs to be freed. All right, it's been an hour. I don't want to hold you guys here for too much longer because I feel it's we're just gonna
I'm sorry, can we take like a 2-minute bathroom break? I can't hold it anymore, but I want to be here.
Yeah, no, exactly. So it's been an hour. I don't know. These are decreasing returns. Let's take a 5-minute break. I'll call you guys back with roosters when we're back, and we'll just keep going. Okay. So go ahead. I'll call you guys when we're ready. No. voice. All right, I was hoping for something a little bit funnier than that, but hey, at least I got you guys here. All right, so this has been great. I'm glad we've been able to answer questions. Let me just get you guys through append and read a little bit faster, just so we can get to truth tables. If there's still any questions regarding arrays, or like still bring them up, don't worry. If we need to, we'll spend more time on this. All right, so next we need to do append. So let's do append. Connor, do we need to return anything from append? If so, what do we want to return?
One second, I was debugging one of my problems.
No worries. So we're doing append now. So every function needs to have a data type that needs to return. What are we going to return?
It can be a void function.
How come?
Because we're actually not going to return anything. We're just going to manipulate the array.
All right. So do you do a void pointer or just void like this?
I don't think we need the pointer.
Yeah, exactly, because we're not returning anything. All right. And then obviously we need the array itself and something else that we need.
The element that we're going to append.
Exactly. Right. So,
or pointer to it.
Yep. Yeah. Particularly a pointer, because like we discussed before. Let's see. Too many drawings. Just what we discussed here before, right? Same envelope, address pointing to the same house, even if we don't have like a copy of the house itself. All right.
I know.
All right. So the first thing we want to do is we want to make sure that there is space for us to append on the array, right? We declared capacity. If the count is over that capacity, then obviously we can't keep adding. So pretty simple. We just do a simple check. If array not capacity is so if the capacity itself is less than or equal to the count, at which point we should stop. Then so what you really should do is resize the array, right? So we just called resize array and resize it. So now now that the array is resized, we can keep going here in append. We haven't so for yesterday, resize wasn't done. So whenever you run into something like this, simply leave it in here, comment it out, and then just print out an error, right? Error, array is full. You're good. And then, oh, this is missing this. And then just return so that your function doesn't keep working and so this is what we have for today. Tomorrow we'll look into how to actually resize. So let's keep going here in append. So the first thing we want to do is we want to create a copy of the element itself, because right now we don't even have the element. So just create a single string loop. So now we have our new version of the element. We're free to deal with this however we want. Remember, this needs to be freed because string loops use malloc under the hood. So every time you string loop, you also have to, for every string loop, there's also an equal and opposite free. Right. Next is we just get array.elements, and well, we have to set it to somewhere. What index do we want to use here? If we're appending meaning adding to the end of the array. Hardware, you want to take a guess?
Count.
Oh, yep. All right. And then we want to increase count since we have
array AR arrow count. But...
Nice, very nice. Yep. And remember, it's arrow, not dot, right? Because we're using the pointer. We're not using the array itself. So arrow count, and then we increase the count because now we have an extra element, right? So we know the next time. So say we appended at 0, count is 0, right? We appended an element to count 0. Now we just want to increment by 1, so that next time that we call append, array.count will be 1, and so we'll append that position. We'll insert into position 1, not into what's the word? Not
Why did you need to use string dupe again?
Sorry?
Why did you need to use string dupe? Do you need to use that? Because mine looks exactly like yours, except mine just says equals element. I didn't do a string duplicate. So I'm wondering what the benefit for that.
I was wondering that too. Why exactly are we copying it if it's already a pointer?
So let me see if I can get this right.
I was watching Brady's lecture, and he mentioned that it was because that way, if the original element gets changed or deleted, it won't give you an error for that array. So he said it was safer than to make a copy than to reference the original.
Yeah. You could reference the original, right? But the thing is, yeah, if you're referencing the original, then you're instead of getting a copy, you're getting right. You guys remember, dark blue is the original, light blue is the copy. So if we make a copy, we own this one. This one is safe. This we can do whatever we want. This, however, does exist there outside. So if for whatever reason, we make some changes to these, and now it's yellow. We're making changes to what we added outside, and that's fine. But if we didn't want to make those changes to what is in our element array, then we're out of luck, because since our elements array is, if we don't make the copy, right? If we make the copy, it's pointing to this, we own it, it stays however we want. If we're not pointing to a copy and instead we're adding, you're adding it to here, we switch this and it'll, basically get messed up.
So it's an attempt at sandboxing, essentially.
Yeah, just being safer.
Okay.
Yeah, you could if you wanted to just put it out there, and if it never changes, then that's fine. It's just safer.
Well, thanks.
Yeah, no, and thanks for that. Thanks for that one, Elvis. I wasn't too sure myself. And all right, and finally, read should have been pretty easy. I'll just walk you through it because I don't think there's too much. If there's any questions, I'll usually have them come up. We want to return a char star because we want to, we're accessing the element. We want to like get it, right? So we're passing the array, the index where we want to read. Let's see, here away. And then easy, right? Do our error check. If index is greater than array.count. So quick question, why are we doing count here and not capacity?
Because the count might be less than the capacity. And if it is, then we can get an error if we go above what the count is. Because the count counts the actual elements in the array.
Yep. We might have capacity for 10, but we only have 5 elements in our array. And then if we try to index number 8, if we compared it to capacity, we'd be fine. But the truth is, our count is 5. We don't have a 9th element there to check. So when we do array 8, we'd have an index out of there. So yeah, we can just printf error index out of range. You can make it more fancy and include the names if you want. For time's sake, I'm not gonna. And then just return null.
There you go, doing the colon thing again.
Oh man, they're on the same key, and so sometimes depending on whether I press key shift or not, it gets stuck. I promise I'm not always trying to trick you guys. All right, and then this is if the index is greater or equal to the array count, because we count at 0, start counting at 0. That's why we use equals and not just greater than. If it's not there, then we just simply return it, right? Elements, and then the index.
Is return null on line 62 the same as doing like an exit?
Yes. Yeah. I mean, if you want to be nitpicky, technically not the same, because exit is working for a child process, and that's giving you an exit code, and it tells you something, and then return is not exiting the program, it's just finishing the function. Return as you keep going. But yes, for the sake of the function, it means the function is over. We're done.
Okay.
So this is not gonna work. Same thing here, right? So if array, if the capacity is less than or equal to the count, the reason we have the return statement here is so that we don't keep going and keep doing stuff. However, we're gonna get rid of it eventually tomorrow when we do resize, because once you do resize, right, and now the array has greater capacity, now you do want to add the elements, right? Like that's why we don't have a return statement after the resize array. All right.
Is there a reason? Of course, there's a reason. Is there a reason why we used where is that? Greater than or equal to in the read? Yeah, when the instruction says throw an error if the index is greater than the current count. So is equal to the current count? Is that why we did that?
So let's think about it this way. If we have 5 elements in our array, how would you access, what index would you use to access that 5th element?
4.
Exactly. So if index is, if we have 5 elements, what is our count?
5 elements is 6.
No, the count of elements.
Wait.
So count is just literally how many, like it's a it might sound tricky because it's so straightforward.
5 elements in the array, then 5.
Yes, if we have 5 elements, our count is 5. So if we do array of elements 5, but there's only 5 elements, you're going to be out of range.
Okay.
Is that clear or?
No, sorry.
All right, so listen, so you could, technically get rid of the greater than,
Oh,
right? Like
interesting.
this is the first part where it's important, because if I've got let's not use yellow.
Because mine works without the equals. That's why I'm asking.
It shouldn't.
The tests just aren't testing for that edge case.
Yeah,
I see. Okay.
it might just not be testing for this. So so number of elements here.
Because originally I did do greater than or equals to, and then I read the instructions, the comment instruction again. I said it just says greater than, so I took out the equals and it still worked. So I'm just wondering why and what I need.
So the thing is, if you do just greater than, right, and here we check like array 100, then yeah, it's gonna break, right? Because like there's obviously not the 100th element, right? Now let's get closer. If we do 6, there is no 6th element, right? And this is still greater than count. Let's see, 100 is greater than count. 6 is also greater than count, so this is going to break. Now 5 is equal to count. But if we do array 5 here, it's also going to break.
Because there's no index 5.
Oh wait, let me sub.
Is that
0, 1, 2, 3?
I'm sorry.
Yes.
I'm spending more time on this. It's just I
Yeah,
wanted
no
to
worries.
buy.
There is no index 5. These are all right. Like if you want to get array 0, there's array 0.
Yeah.
All the way up to array 4.
Yes.
Is the 5th element. If you do array 5 here, you're going to look for some element here that's not there. That's why you include the greater than sign.
Oh no, the greater than I get. It was the equals. I was.
Yeah, sorry, my bad. That's why you include the equal to sign.
Okay.
All right.
Thank you.
Yep. All right. Cool. Any other questions regarding arrays? I know it's a little bit rushed, but like don't worry, guys. If you have questions, don't worry. With truth tables, we can get through a little bit faster. There's a cool trick I'm going to show you anyway. All right.
Is there truth tables in the assignment, or is there an assignment with truth tables?
Actually,
this is just kind of a theory thing we're just going over.
I'm actually not sure. It seems like, yeah, might not. Maybe tomorrow. I think there might not be. I'm not entirely sure right now. I haven't checked.
They come in handy when you're trying to suss out edge cases for a particular algorithm, but
if I recall, because I've been through this part of the C stuff, if I recall, there are truth tables in the sprint.
Okay. Are we making logic gates? Are we making logic gates in the sprint?
Remember correctly. I don't remember the specifics, but I do remember there were a few.
Okay.
All right.
And Luisan's tricks are really nice.
Oh, I'd love to take credit for this trick, but
they got me through a good part of FSW.
All right. So, okay, sorry, we're good with the race. Nobody had any more questions. I was just looking through. I guess it's no. All right. Again, also know. I mean, we're a little bit short in time, but obviously, always around to help if you have any questions regarding arrays or the homework. I'm going to drop the solution code in the channel after we're done. All right. So there's a few things to talk about regarding logic gates and transistors and how these work, and just what's going on. Let's see. Let's go over them quickly. So again, let's see. A computer reads zeros and ones, right? Man, I really, really, really love this resource. I don't want to get you guys tired of watching it over and over again, but I think this is really good, right? Your computer is zeros and ones, right? It's made up of blocks of bytes that hold zeros and ones. Each of these bytes, though, holds 8 bits, and each of these bits themselves, they hold 0 and 1. Now, how do we actually represent this in a computer? It's on or off.
Electricity.
Exactly, right. Just electricity, it's, you know, like either it's on or off. It's either running there or it's not. And so to do that, we have these things, you've probably heard the names before. These are transistors, right? Like, okay, so I was going to say, please don't ask me any questions. Actually, yes, do ask me questions. Just, I don't know the details, right? Like, no electrical engineer, I'm not entirely sure how this is supposed to actually work. But, you know, electricity comes in on one side. I'm not entirely sure what the side in the middle does. I think it just helps to decide whether electricity goes through or not. And then one side, either energy comes in, either energy comes out, or energy doesn't, right? And that's your 1 or your 0. Energy is coming out, that's a 1. Something's happening. Energy doesn't come, that's a 0. And so what you get in a computer is just like, you know, billions and just like ridiculous amount of numbers of just zeros and ones, which end up building, you know, the computer you're looking at right now, right? We now have, so this is obviously quite big, right? Like you can grab this with your fingers and you can check it out. Your computer is obviously not built with this. Your computer is built with these guys, right? These are, let me get you guys out of the way, integrated circuits. And what these do is they're just like a huge amount of like mini, like tiny transistors here. I found a pretty cool like electron, here it is, check this out. This is, you see this is like 10 micrometers, right? And these are all, I can't tell like which one is transistors, but like this is the level at which we're dealing with right now. Like this is the size of the transistors we're building. This is the scale at which we use them. This is why you get to fit so many of them, right? You guys, I know we probably don't have to talk about this, but you know, just Moore's law, right? Like they started out, oh, where did I lose the transistor? Started with transistors, right? They're pretty big. According to Moore, they're just gonna get like smaller and smaller and smaller and cheaper and cheaper and cheaper. So here it is, yeah. So I mean, yeah, the obviously moving up and right doesn't sound like smaller and cheaper. It sounds like more expensive and bigger. But what this is referring to is the number of transistors on an integrated circuit chips, right? So take a look at these numbers here. What it is, like 10 billion, almost 20 billion in one of these guys, right? They're tiny. And what these do is just, you know, give you the option. Do we go yes or no? I know we're kind of speeding through this, but the most important thing we're going to deal with are truth tables. Let's see. Actually, let me bring up some other truth tables. So you've all seen this before, right? Truth tables. This is a good one. So this is P. It has some values. It has true or false, true or false. Q, true, false, true, false. This is just so you can see difference. Let's see if we can find number one. This one is nice. So this symbol here stands for AND, right? So what this means is we will only get true if both the inputs are true, right? So we get 2 inputs. If both of them are true, then we get true. If either of them is false, then this thing is false. And so you can see here, right? We have two inputs, true and true. If both are true, then the output is true. We have two inputs here, true and false, false and true. Since in either case one of them is false, then the result is false. This case, both are false. Since either or one of them is false, and this returns false, and we get false. And so this is just with truth tables, what your computer can build is just the complexity grows hugely. What we saw here is an AND table, right? The opposite of this is called the NAND table. And so NAND tables is basically just the reverse. Let me have them side by side. If true is 1 and false is 0, you can see that an Angus is just an inverted AND gate. Literally, if you have 0 and 0, it's 1, 0, 0, here is 0. 1, 1, 1, you can see the results are just pretty much switched around. And so
basically, if it's true, it's false, and if it's false, it's true.
Yeah, just whatever results you get from AND, you can flip them around, and then you get not AND, right? The negation of AND. Let's see. When you negate something in truth tables, you get the opposite of its value. So remember this one, right? You have P and Q. P, we're giving the values true, true, false, false. Similar to what we're looking here, what we're seeing here, right? Just seeing the different combinations of inputs. Not P just means the opposite of P, right? So whatever P brings, not P is going to bring us the opposite. Same concept for AND, right? True, false, false, false. This one is just upside down from what we see in Wikipedia, but it's just negating all of the results from AND. 0 and 0 would be 0 in AND, so we turn it around, and it's not the result, right? It's the opposite, so we get 1. Same thing down the line. Now, I am not particularly an expert in figuring out how. So apparently you can, here it is. Because NAND function has functional completeness, all logic systems can be converted into NAND gates, meaning you can do not, and, or, nor, XOR, or XNOR, or just like all logical combinations you can create from a NAND gate. I'm not super sharp on knowing like how to create them straight away, but if you can take the time to read through it, yeah, you can do it in you can read through in Wikipedia and see how it works. Let's take a simple one, for example, right? A NOT gate. You do A and not and A, and you're simply just whatever the input is, right? You're negating, right? Like, right? A and not A, right? Say input A is A, input A is A, then the output is B, right? Let's see. These two don't apply because obviously it has to be, because since A is going to be the same, it has to be the same on both sides, right? Like A and, or I guess not and A, right? You get A and A, then in your not and, your response is 0, and I mean, this is what you see right here, right? And so I don't know these by heart. I know how to calculate them using Python. I'm going to show you that in a bit, just before we do some exercises. But yeah, you can build all of these, and somebody correct me if I'm wrong, but apparently, if I read this correctly, your entire computer is built using NAND gates.
Yep.
Is that right?
Mm-hmm.
Awesome.
Yeah, There used to be like specialty chips that weren't using NAND, but as far as I recall, pretty much the entire industry has shifted over to the generic NAND based ones just for cost efficiency and stuff.
Right. Yeah, I mean, obviously you can, there's different, I guess, different ways of writing all these. Like you could just write them out on their own. But since you can make them by NAND gates, Via can probably tell you better than I can, but apparently it's just worth building your computers exclusively with NAND gates to just build everything else. Now, I want to show you something that helped me, because I remember looking at this and thinking, all right, yeah, cool, there's a bunch of transistors here, right? I can see they're tiny, they're all over my computer, and you know, I have truth tables, and these make sense, right? I have some input and some output, and then I get zeros and ones. But like, how does this actually? How does these actually look? Like I can see this here, I can see the diagram, but the diagram doesn't tell me anything about like how the electricity itself physically is moving around. So I found some representations, not for all of them, but I found some that are pretty cool, that I feel really help paint the picture. Let's see, 1 second. Here we go. So say this is an AND function, right? And so let's bring a truth table right next to it. Right. So it's bigger. Oh man, all right, we'll have to. Perfect. All right, so we said, right, these are zeros and ones, right? They're electricity ons or offs. In Wikipedia here, like 0 and 1. So 1 is electricity is flowing, 0 electricity is not flowing. It's just like either turned on or it's turned off. So check it out here. I don't know if you guys in case you haven't seen circuits before. I know I only did like in college. I never like because I was doing something related to engineering. But if the circuit is closed, then electricity can flow through, right? Think of it like a pipe with water. If something is open, then like electricity leaks out and you don't get to turn on the light bulb, right? You've seen it if you like grab the cables together from some light and you touch them together, then electricity flows through, and then you can turn on the light bulb. If they're not touching, then it's off. And so now, what I really, really like about this, the way this circuit is designed, is it makes it really obvious, right? If you want to have an on, right? If you want to have a true, a 1, then you need to have both A and B closed. Otherwise, the way this electricity is flowing, if you open A, then let's see how we can do. Finally, have some use for yellow. So if we come in here and it goes through A and A is open, then boom, you're just gonna get out. It doesn't matter what B is doing, right? Because like since A is open, then the electricity is gonna flow out. Let's go back, bro. Let's say A is closed, right? So A is true, but B is still false, right? Then we're gonna come here, electricity is gonna come, it's gonna flow through A, it's fine, and then it's gonna go to B, and it's gonna fly out. And so this is gonna stay off. This is gonna always be a 0. So the only way it's gonna work is if, like an AND table, right? It's only gonna work if both A and B, hence the name AND table, are connected. And so let's see, here's the yellow. And just so we can get the satisfaction of seeing it come through, here's the electricity, or just it takes a look at A is true, it's on, so it keeps going, it shows up to B is also connected, so it's going, and then yeah, finally the electricity can flow through. And this is so, the shape itself, it might not be like exactly a square like you see right here. I haven't ever built a computer or transistor chips or had anything to do with it. But in essence, right, like in order for there to in order for there to be an AND gate, it has to look something like it's represented as something like this, right? Something where both A and B are important for the electricity to flow. Let's check out other examples. What was this one? Before perfect. Here we go. So we'll make this big one again, and then in here we'll get OR, right? So this symbol right here, this is the OR symbol, all right? And so now take a look at this one, right? If both A and B are open, then we'll get the same thing happening, right? It'll come here, it'll try to go through A and it'll leak out, it'll try to go through B and it'll leak out, and you'll get nothing, right? 0, 0, you get 0, right? Pretty easy. Now, let's say, now the cool thing here, right, it being an OR gate, is if we close either one, then the circuit is closed. So say we close B, then that's fine, right? A is gonna, so electricity is gonna come up here, it's gonna look through A, it's gonna see, oh, it's leaking, so I'm just gonna stop. I'm not really gonna go there. No idea how electricity does it, but I do know that if the circuit is not open, it won't flow. But then since B here is open, you see we have a closed connection here. Like this is a closed loop. And there you go, right? A might be false, but since Q is true, we get true. And then I guess we don't really need to walk the other way around. But if we close B, if we close A instead of B, it's going to be the same thing. And if we close both, then obviously, right, like, yeah, the entire thing is closed. And so we get true and true set to true.
Great time to mention XOR.
I forget about that one. I'm not too, let's see.
Exclusive OR. Basically, it's one or the other, but not both.
All right, so there's a bunch, right? So let's see, here's XOR, right? There's a bunch of different, we're gonna go through some of them in a second. I don't have drawings for all of them, right? I'm not entirely sure how to figure all of them out. These were the ones that I could find. XOR is, yeah, one or the other. So it's either A, it's either B, or it's A. So if it's one of them, it's true. If it's neither of them, it's false. If it's both of them, it's false. There's XNOR is just the opposite, right? It's either both or none. But if there's one of them, then you get rid of them. I can send you guys this link, or you can just search for NAND logic gates. And just then let me show you the last one. Oh, the NOT function. This one is pretty nice. Yeah. What is this? All right. So this line up top means not A, right? So if not A, let's see. This one up. Let's get rid of you guys. And then you can forget about these guys. All we're thinking about is it's not aggressive. All right, we're thinking about P and not P, right? So this here is not P. This is going to do the reverse of whatever A is doing. So if we close A, it means that we're closing this, but instead we're opening this guy. So when electricity comes, it's going to be, when A is set to true, it's going to come here through the resistance. It's going to hear this point. It's going to be able to flow here, right? And flow here, it's just going to come back. right? Whereas when it comes here to this not A, it's just gonna leak out and it's never gonna get here. Same thing in reverse, right? If we have not A, which means that the not A is closed, but then, right? So like here, this is A being false, so not A is true. So in this case, A is open, so not A is reverse, it's closed. Same thing, right? Go through resistance, and it'll be able to do the walkthrough. You know, being able to see it like this and making the connection really helped at least me understand, like, okay, so there's some sense to this now, right? Like, I know there's transistors, I know there's these tiny things, and they do like zeros and ones. How the hell do they get converted to truth tables, right? Like zeros and ones and all these combinations. There's just like a bunch of different shapes for each of these. If you see it here, these diagrams are not illustrative because they just tell you different shapes of what each means, but there's like real physical shapes of how the electricity flows. Any questions so far, or we can spend just the last 5 minutes looking at some truth tables and me showing you how to figure them out with Python? All right, cool. So just gonna just get out of the way. Two things. Let's see. So let's just we'll fill this one out ourselves. Let's do it. We'll do this manually. So you guys help me fill this out. So we have not A or B. Okay. So what would the result be here? I guess, Zach, you want to take a guess?
That'd be a 1.
Why?
Because we have a not A. So, right? Yeah, makes sense. So A is 0, which is like the false, basically. And then we don't have, and then B is false, but it's an OR, so we have the not A.
So if you want to right here, A is 1, right? And since, like you said, it's an OR, so the result just turns into a 1. Easy. All right. Alvis, do you want to try the next one?
Yeah, I think that one's a 1, since there's a 1 and we're doing OR.
Yep. Turns out minus A is also, negative A is also 1, so you also get this. Perfect. Right. Let's see, Hargo, you want to try a third one?
That would also be 1.
All right. Why would it be a 1?
Or actually, no. That would be the only one that would be 0.
Yep, that's exactly right. Tell us why, please.
Yeah.
Why would it be a 0?
Yeah, because A is not knotted, or is flipped. So then B is 0. So then the result would be 0.
Yep. And then I guess Chad, this last one.
Let's see. 1 and 1.
Which turns to 0 and 1, 0 or 1.
0, 0.
So 0 here.
Yeah.
Almost, not quite. So it's negative A or B, right? Negative A is 0, B is 1. So it's 0 or 1. What does 0 or 1 give?
let's see, 1 and 1. So 0 and 0 is 1 and 1. 0 and 1 is 1 and 1. So 1 and 1. It's I'm not sure.
All right, let's do it. So this is what you're looking at, right?
Yeah, this is
We're
this
looking
is
at this.
the not or.
No, this is just something else. This is one we're just making up ourselves. This is just
Oh,
filling out
okay.
any truth table. This is not a specific one.
Oh, okay.
It doesn't.
Okay.
I mean, it doesn't really matter.
Okay.
So here we have negative a, not a or b. So what's the value for not a? In this case, this last case.
The value of not a is 0, right?
Yep. All right. So that's a 0 there. What's the value of b in this last case?
The value of b is 1.
All right. And since this is an OR statement, then what result do we get if we have 0 or 1?
1.
1 then.
Yep. Exactly right. Pretty easy. All right. Now, obviously you see this, like these start getting crazy, right? Like how the hell am I gonna check all of these? We could. It's possible, right? Like it's actually not that bad. It's just a few of them. But there's a much easier way we can use with Python. So let me show you. So the way I like to do it is I set a little just truth array. Actually, let's call it T array. And then this array has false and true. Now, we're using A's and B, right? So we do for A and T. And so this loop loops through false and true for A, gives A the false and true values, right? And then for B, same thing. So now I have a combination. It's going to be 4 of them, right? False. So A is false, B is false and true, right? So that's one combination. That's 2 combinations. Then A is true, and then B is false and true for A. Pretty simple. And so, say for this one here, what we would simply write is Python is great at this. Print not A, which is what we see here.
Got an extra T in your print.
Thanks. Print not A, right? Then our next operator is OR. So we literally just write that one down, OR. And then B, right? Print not A or B. And so A is going to come in as false, and then we're going to check not false or false for B, right? Then A is still false, B is now true. I'm going to check not A, so right, so not false for A, and then B is now true, or B being true, right? And then it's just going to print out whether false or true. And so let's see it in action. And there you go. You see that? True, true, false, true. Still with numbers. Whoa, this also works. I'm gonna actually, my bad. Seems like it will always work. But yeah, you guys can translate true to 1, false to true. Let's see. Let's try another OR table that we don't have answers to, just so you guys can see.
Let's try that pointy guy with the 3 arguments.
Sorry?
Let's try that pointy guy with the 3 arguments in there.
This one?
I think it was number 3, yeah.
We're going to do this in a second. I just want to show you with some other truth table that this does work. I don't know Python for X or, but let's just do an AND table. That one's easy. All right, so A and B. returns true if both A and B are true. If only one of them is true, then it returns false. False, 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 and then when both are true, you get true. Simple as that. Now, the cool thing is, now you can do it for all of these crazy things. So let's take a look at this one. Let me bring it over here. It's a little bit easier to see. All right. So print not A and B, right? And not A or not B, which makes it a little bit bigger. Right? So not A and B, A and B, and not A or not B. Print that. Of course you can't be there. There you go. Always false, right? And then let's do this. All right. And so if you want to add a third one, all you do is just add another loop in there for C and T. Make sure you call it right so that it knows where it is. It's Python, remember the indent. And all right, let's try writing this monster out. All right, so print A or B, or we open up parentheses, and then inside this parentheses, it's not A or C, or not. All right, so we're at a not here. Not B or C. This is another parentheses. I don't need this extra one. So these two fit together. These two fit together. These two fit together. Now we just need the Python 3 print parentheses. And again, here we go. Print to 3. You see 2 for all of them. You see as well, you get 8 results like you'd expect. All right, I guess any questions, comments, concerns? I need to come up with a new phrase.
That was really cool. I don't think they ran through that with us as detailed when we went through it.
I really hope this helps. All right, well, I'm gonna paste this. So this cheat code for Python, I'm gonna paste it in so you guys always have access to it. It's just gonna make stuff so much faster. Always, rather than trying to figure out like one by one. For the sprint, though, I would recommend. Get the hard part done first, where you have to do all the code. I think there's going to be a Q&A part where you use this. Definitely use Python to check, but also check manually because we might be making some mistakes, right? Like right away, I see all these trues here, and I'm a little skeptical. I'm not entirely sure. I might have made a mistake somewhere here or there. So you always want to check. This looks a little too good to be true, even though it says true so many times. Just make sure you check, right? Like Python is not going to make any mistakes, but you might, and you want to be sure you didn't. Other than that, for today, pretty easy. Knowing what to do is pretty easy. Just to insert, remove, and resize array. And then there's 2 things you can do. So once you have insert done, insert is like a more general version of append. So, come on, I thought we lost this. So array append can just turn into, like array insert with your element, and then I guess the index might go first. I'm not sure how you want to build your index, but So you just, instead of the index, you put the count, right? Knowing that you're gonna set this up here. So actually look like this. And then your element, right? So that's one. And then once you do implement resize array, I want you to use it inside your append, and well, technically inside your insert, since you're going to be using insert for the append. But I do want you to be able to resize the array and have that work. It should be part of the what's the word? Should be part of the tests written down in the repo, right? I'm going to drop all this code. I'm going to upload yesterday's video, which I forgot. I'm going to upload today's video as well.